Hi class, this video is on topic B8, elastic and inelastic collisions. So by the end of this video, you want to be able to compare and contrast elastic and inelastic collisions, describe each in terms of what happens before and after with momentum and energies, and solve calculation-based problems. So in this chapter, we've been talking about collisions, or when one object in motion comes into contact with another object that may or may not be in motion. And we can talk about collisions on a very small scale, like gas molecules colliding, or on a very large scale, like stars or asteroids. And one example that we'll come back to in this chapter is the collision between two billiard balls. So I want you to have that as a visual. In this chapter so far, we have learned that momentum is the product of an object's mass and velocity, and that it's a vector quantity in units of kilograms meters per second. And we can find total momentum of a system by doing the vector sum of the momentum of each object in the system. We've also, in our very last video, talked about the conservation of linear momentum, which states that whatever momentum is lost by one object is gained by the other. And in other words, the total momentum of the system is conserved. Conserved means constant or not changing. There's a condition on this that no net external force acting on a system to make it an isolated system, but most collisions happen over such a short time interval that the action-reaction forces associated with the collision are much more significant than any gravitational or frictional forces. So in this course, momentum will be conserved in all collisions and explosions. And here's the visual. So a reminder that the word interaction from that law of conservation of momentum can mean different things. So the interaction can mean a collision where objects bounce off, like billiard balls, or it might mean a collision where the objects stick together after, like a running athlete catching a ball and continuing to run, or it might mean an explosion where one object turns into two or more objects. So to further characterize these different types of collisions, an elastic collision is a collision in which two objects bounce off one another. And in elastic collisions, the total momentum is conserved and total kinetic energy is conserved. Specifically, perfectly elastic collisions are idealized collisions in which external forces are minimized to the point where both momentum and kinetic energy are perfectly conserved. So technically, when we say elastic, we mean perfectly elastic. In elastic collisions, objects return to their original state after the collision, and returning to the exact original state and perfectly conserving momentum and kinetic energy. It hardly ever happens in real life, but a close enough example will be the two billiard balls in the pool and other elastic collision examples that we'll do in the homework problems. So an inelastic collision is a collision in which only momentum is conserved. Kinetic energy is not conserved. The objects can be permanently altered. They do not return back to their original state after the collision. And an example is a collision between two moving cars. Perfectly inelastic collisions happen when the two objects stick together and then they travel as a single unit after, therefore having the same final velocity. This is very nice in the way that it simplifies our momentum equation. So there's some simplifying that happens that is convenient when we have perfectly inelastic collisions. Total momentum is conserved, total kinetic energy is not conserved. So think about visualizing a perfectly inelastic collision or an inelastic collision. Where might this lost energy have gone? So it might help to think of a car crash, which is an example of an inelastic collision. If two cars stick together after they've crashed and move together as if it was only one object after the collision, or maybe they don't move together at all, they're now at rest. In this inelastic collision, each car started with kinetic energy before. What type of energy was present after? So some energy might be in the form of kinetic if the two stuck together do move, do have some velocity. However, what are the other forms of energy? Because if energy after of the combination is not equal to the sum of the kinetic energies before, then kinetic energy is not conserved. There's lost energy. So where does that go in the car example? So as you might have guessed, we've got sound, heat, and the internal energy of the system as the car bodies deform. So have you ever heard of crumple zones? There are these areas of the vehicle that are designed to crush in a controlled way and therefore protecting the passengers. They increase the time it takes for the change in momentum of the car, of each of the cars, and of each passenger, so that reduces the force. So to crumple the body of a car, it takes work. In other words, it requires energy. Therefore, some of the kinetic energy of the initial objects before the collision would be used in that crumpling. And if you haven't seen a picture of a safety crash test, here it is. You can see the crumple zone if we're talking about the front of the car. So the amount of kinetic energy lost in the inelastic collision depends on the objects and the conditions. And as Professor Dave says, and he is linked in this video below, in real collisions, we'll actually get somewhere in between. So it's actually a spectrum between perfectly elastic collisions and perfectly inelastic collisions. And real collisions are in between. So not all kinetic energy before goes into the kinetic energy after, as in a perfectly elastic collision. But not all the energy is lost. So not all that kinetic energy that is in the initial diagram of the two objects turns into lost forms like sound and heat in a perfectly inelastic. We can often simplify to be one or the other, or we can just accept in between that we say inelastic, and we know that it's not all the energy that is lost. So for our purposes, we are always going to use the law of conservation of momentum, but we're going to question whether or not kinetic energy is conserved. So just know that it may be some kinetic energy lost or all kinetic energy lost. So let's do a practice problem. So in example 1, we have a 60-gram dart striking a stationary 200-gram apple, and it gets stuck. Let's assume that there was a decimal here and here, and that this is 2 significant figures and 3 significant figures, just for the purpose of practicing our significant figures rounding at the end. So what is the final velocity of the dart and the apple? So the dart gets stuck and they both move. What's that final velocity of the combined masses? And what is the change in the kinetic energy of the system? So let's go to that solution. So in this case, it's always really important to draw a diagram before and after. So if you don't have that, draw that in, practice writing out your before and after collision, and label your givens. Noting that we don't have SI units, so maybe right away out of habit, we're going to change it, out of this good habit, we're going to change to SI units. And we do have a collision, so we're going to write a law of conservation of energy statement. Luckily, we can simplify that the apple is at rest before. It says a stationary apple. So this whole term goes to 0. And then also, luckily, in terms of not luckily in terms of this apple, but in terms of simplifying this equation, the dart gets stuck in the apple, which means that the terms at the end, VF1 is equal to VF2, so we can factor out the VF, and we're left with V1 V1I, M1 V1I equals VF times bracket M1 plus M2, and we can simplify VF. So we simply sub in 0.06 kilograms times 12 meters per second. It makes sense in this diagram to assign whatever direction the dart is initially to be positive, because that's the only direction of motion before or after in any of the objects. Substituting in the values, we get 2.76 meters per second. That's positive, so it means to the right, or we'll say forward. And we'd say that therefore the dart and the apple have a final velocity of 3 meters per second forwards. Part B is, what is the change in kinetic energy of the system? So question, could it be 0? So pause this video and ask yourself, could the answer to B be 0? Okay, if you said no, it cannot be 0, you're right. It cannot be 0 because the dart gets stuck in the apple. So we know it's inelastic. We know we lose kinetic energy. So to find out how much kinetic energy we lose, we can find the initial kinetic energy of the dart and the apple. And we can subtract the combined kinetic energies, or sorry, the kinetic energy is of the dart and the apple at the end, the final kinetic energy, and subtract the initial kinetic energy, which is the sum of the dart and the apple's kinetic energies. But since the apple was stationary, it goes to 0. So we substitute in our numbers 1/2 mvf squared for the after diagram minus 1/2 vi, this should say squared here, squared for the dart in the before diagram, and we get negative 3.323 joules. So final minus initial gave us a negative, which means we lose kinetic energy. So, and that's the energy that we've lost. The kinetic energy that we've lost, we decreased by 3 joules. I suppose when I drew this up, I saw one significant figure in the 6 of the 60 and the 2 of the 200. So I suppose I rounded it to 1 sig fig here. Otherwise, if you considered it was 2 sig figs, it would be 3.3 joules lost. And this is considered an inelastic example because the dart gets stuck in the apple. So let's go back to our slides and continue on. Oh, we have a visitor today for the holiday weekend. Our second example is we've got two carts, a 2-cart collision. So a 2 kilogram cart is moving at 8 meters per second right, and it strikes a 5 kilogram cart originally at rest. So at rest. The collision is elastic. Find the velocity of each cart after the collision using the conservation equations. So if you try, at the end of this video, you try the practice problems and you are stuck with page 236, number 1, this is a really good example for you to refer to. Always start your collision problems with a before and after diagram. So this is not, maybe this could count as the before diagram, but you need a before and after diagram, label all your givens, set a positive direction, and question what type of collision you have before you start the problem. It says elastic. We highlight our givens. We use it to label our diagram. It says the collision is elastic, which means that momentum is conserved and kinetic energy is conserved. And there's also another hint that energy is conserved because it says using the conservation equations. So we are going to set up the before and after diagrams. Actually, I'm going to speak about this diagram step by step.
But B8, elastic and inelastic collisions. And this is example 2, the two-cart collision. So
it's important to start all the collision and explosion problems with a before and after diagram. So I've just drawn a red cart and a green cart before the collision. With the red cart has 8 meters per second velocity to the right, and the green cart has a velocity of 0. And then I've drawn a possible scenario for the collision after. I've labeled all of my given information. It's really important to do that before and after diagram, and also establish what is going to be our positive direction. So you can arbitrarily select right or left in this one-dimensional collision to be positive. So I'm going to say that to the right is considered positive. So my V1I, which is the initial velocity of object 1, is going to be positive 8 meters per second. One possible scenario is that the red cart moves left after, and the right cart moves to the left after, and the green cart moves to the right. So there's the possibility of solving for speeds, and or we're going to be able to solve for velocities of each of these objects using what we've learned in this lesson, which will give us the speed and the direction after. So we're not set on the direction that we decide in our after diagram, but we're going to put it in because we don't want to forget to think about direction. So it's really important that we start the problems with the collision problems with the conservation of energy statement fully, unlike the textbook solution does. So the textbook solution jumps to simplified forms, and we always want to start with the full law of conservation of momentum statement. So we know that M1 V1I plus M2 V2I is equal to M1 V1F plus M2 V2F. And we're hoping to simplify this. We know in our collision problems in this course, we're going to say that momentum is conserved, which if the collision time is short enough, then we can make this law of conservation of momentum statement. But there's also a key word in this problem. The collision is elastic. So because it says elastic, we're also going to be able to use the conservation of kinetic energy if we need it. So let's simplify this and see if we need it. We know that the initial velocity of object 2 is 0, so that whole term cancels out. And if we just check off, do we have enough information to solve? So we have M1, we have V1I, we have M1 again, we have V1F, we actually don't know, and V2F, we don't know, and we have M2 because it doesn't change. So we have M2 and we have M1. There are 2 unknowns in this statement, and there's no other way to simplify it. Therefore, we know we need to be able to write. Okay, so using our conservation of momentum statement and simplifying as much as we can, noting that we have 2 unknowns, and that we'll have to combine with that with another statement from our energy conservation. I prepped this equation 1 by isolating V1F. It doesn't matter if you isolate V1F or V2F. I just picked 1. I'm noting that there are 2 unknowns. And when you work with a conservation of energy statement and you realize there are 2 unknowns and there's no simplifying or subbing that can take you further in the question, that's how you know that you have to call this equation 1 substitute one of the variables, and then move on to the energy conservation. So because it says elastic, we can write the energy conservation. ET before equals ET after. And we know total energy, total mechanical energy is made up of different types of potential and kinetic energy, but there's no changes in the potentials. So the only change, the only total energy we are talking about considering is the kinetic energy. So the kinetic energy of the object 1 before, plus the kinetic energy of object 2 before, equals the kinetic energy of object 1 after, plus the kinetic energy of object 2 after. Simplify it. We know that since object 2 is at rest before, that goes to 0, and we can substitute 1/2 m1 v1I squared plus, or actually equals, because we removed that term, equals 1/2 m1 v1f squared plus 1/2 m2 v2f squared. Taking a look at what we have and what we don't know, what we can simplify, we can cancel out the 1/2 because it exists in all terms. And we are trying to solve for v1f and v2f. Those are the same two unknowns. So just like in grade 10 solving a linear system, except it's not a linear system, but we can still use substitution. Let's isolate, what options do we have here? I guess we could isolate VIF as well from the energy statement. But we'll have an ugly square root in there. We can just call this equation 2 and sub equation 1, which already has v1f isolated, into equation 2. So that's what I'm choosing to do. m1 v1I squared equals m1 v1f squared, but v1f, we're going to make the substitution. So why are we making that substitution? We've eliminated v1f, which is not known, and we only have v2f that is not known. Everything else in this equation we have. So I am actually going to suggest the one time in this course that we're going to substitute in our numbers. And it's going to clean this up a lot, because if you can see moving forward, this would be a lot messier if we worked with all of those variables. So I'm going to allow you, in still maintaining good form, to substitute in the numbers. So I'm going to substitute in to this equation with numbers, so it's not so messy. 2 kilograms, which is m1, times positive 8 meters per second squared, minus 5 kilograms times the v2f that we are trying to solve for, divided by 2 kilograms. That's going to simplify to 8 minus 2.5 v2f. So that is my equation 2. So instead of this messy equation with a lot of variables, I'm going to allow you to substitute in the numbers into equation 1. And I am going to sub 1 into 2, but I'm going to use equation 1 with the numbers substituted and simplified. So now we go back to our conservation of energy statement. We have M1V1F squared equals M1, and now V1F is 8 minus 2.5 V2F squared plus M2 V2F squared. So normally I don't want you for form to have a combination of numbers and variables, but this is a messy enough type of problem that that's fine. So we're going to sub in the rest of the numbers. Okay, so I've moved over to the other page. These problems are longer problems. In a few videos, we're going to talk about a shorter way to do these problems, but for now, doing it using conservation of energy and momentum is a really important way to solve these problems. So it's a bit longer, change to the next page. I rewrote that line and cleaned it up a bit. So now, just checking in, I used conservation of energy and conservation of momentum, combined those two statements to create this new equation, and I still have V2F, which is the only thing that's unknown, which is where I want to be, and now I'm just going to distribute this bracket, and we're going to be solving a quadratic in order to solve this problem. To collapse this and simplify this, I'm going to call that V2F that we're solving for X. So I can see that it is a quadratic that I'm going to solve. 128 equals 128. When I distribute the final brackets, luckily I get 128 on both sides. And that doesn't always happen. In fact, it rarely happens. Which means that I'm going to be able to use greatest common factoring to solve for this. So the greatest common factor is 17.5x, and I'm left with x minus 4.57. If at this step I do have a plus c term, so the 128 doesn't cancel out on both sides, I would have to go to my quadratic formula, or I would allow you to go on Desmos. So that if this was an online quiz and you're going to have to show me the full solution anyways, so it's just saving you the quadratic formula step, you have my permission to use Desmos for the purpose of solving a quadratic. And then you would get a form where you can solve your quadratic, you know, your two solutions, your two values of x that would make that line true. So we know that one answer, the valid answer that we want to report, is 4.57 meters per second to the right. And we'd report it to 2 sig figs for our final answer. Now that's one part of the final answer. What about V1F? And when we do these problems, you have a system of equations and solving for 2. Once you get the first one, the second one is very easy because then we just have an isolated formula, and we can sub in our newly calculated value. So getting negative 3.4, oh dear. So finding V2F as 4.6 meters per second, we used the unrounded version of that number to sub into what we called equation 1 to solve for V1F, and we get negative 3.4 meters per second. We look back to your original diagram, we said that right is positive. So that negative means that our V1F is equal to 3.4 meters per second to the left. Again, as long as your diagram is very clear with right and left, with what's positive, either right or left, you can use arrows as long as things correspond to your diagram rather than using the word to indicate the direction. So looking back to our diagram, or not, looking to our final answers, doing the common sense check, we did guess that one object would fly to the right and one object would fly to the left. The object that has more velocity is the green object. So I want you to take a moment to think if that does make sense. But direction-wise, we're doing a common sense check. It does make sense. We have two significant figures, and we checked our unit. Okay, so again, it was really important that we had our before and after diagrams, labeled givens. You will be assessed on conventions. So things like a clear diagram, establishing the convention for positive direction, reporting your final answer with the right number of sig figs units, and direction if I'm asking for a vector quantity. It says find the velocity, so we did need to have direction in our final answer. I want to mention before we move on from this question, that was a really long problem. So during these practice problems, you will have to do it this way. There's actually two different ways to solve this problem where you have to use, for an elastic collision, we're gonna soon learn a shortcut to doing this, but unless you're working ahead, you're gonna have to do it the long way with conservation of momentum and conservation of energy. And it's really good practice because that, substitution for solving a system of equations, it comes up so much in this course. So don't think of it as unnecessary work. It's good practice for other kinds of problems that we won't find a simpler way to do. So in a future video, we're going to learn specialized equations that could be used to solve this exact problem. So now it's your turn to do some practice questions. If you are really stuck on page 236, number 1, I encourage you to look back to example 2. If you're really stuck on page 238, practice number 2, I encourage you to go back to our example number 1. And don't forget to be completing the tasks that are assigned on Google Classroom, and to complete all tasks, whether it's a video lesson or if it's a summative quiz. So please be mindful of the deadlines for that. Have a great day.